Classification with mfeat factors dataset. In this lesson, we will solve a handwritten digit classification problem using the mfeat factors dataset from OpenML. The goal is to predict which digit, 0 to 9, an image represents based on 216 numeric features. This is important because digit recognition is widely used in fields like document processing and computer vision. You will learn to load data, explore it, train a simple classifier, visualize results, and understand some common pitfalls. Let us get started on the journey from raw data to predictions. Running the cell now. We import NumPy for numerical operations. We import pandas for handling tabular data. We use fetch_OpenML to load the mfeat factors dataset from OpenML. We import train_test_split for splitting the data into training and testing sets. We use logistic regression as a simple model for classification. We import accuracy_score, classification_report, and confusion_matrix for model evaluation. We import standard scaler for feature scaling. We import matplotlib.pyplot for plotting graphs. We import Seaborn for easier and prettier plots. We use warnings to filter out unimportant warning messages. We set the random seed to 42 so experiments are repeatable. Running the cell now. Try running this cell. Why is setting a random seed important? Understanding our dataset, mfeat factors. The mfeat factors dataset consists of 2,000 handwritten digit samples, each described by 216 numeric features. Each row represents a single-digit image, processed into numeric values. The class column is our target, representing digits 0 to 9, labeled 1 to 10 here. There are no missing values, and all features are numerical, so pre-processing will be straightforward. Beginners often mistake the target labels, 1 to 10, for pixel values. These actually stand for the digit class. Another mistake is skipping scaling. With 216 features, unscaled data can confuse many models. Running the cell now. Let us load the mfeat factors data directly from OpenML. Now we will print the data frame shape and a preview so you know what it looks like. We use fetch_OpenML to download the mfeat factors dataset and convert it to a data frame. We assign the data to the df. We print the shape to see how many rows and columns we have. We display the first few column names to get an idea of the feature structure. We show the first few rows for a quick visual inspection. Running the cell now. The output confirms that our dataset has 2,000 samples with 216 numeric features plus 1 a class column, totaling 217 columns. Notice the feature columns, ATT1, ATT2, etc., contain numeric values describing each handwritten digit, while the class column represents the target digit label from 1 to 10. This setup shows the dataset is ready for analysis, with clear separation between features and target as emphasized in this lesson section. Inspect the first few rows. Can you identify the class column? What do the features look like? Let us check the distribution of classes, digits, to be sure our data is balanced. We print the counts of each digit class to check if all classes are equally represented. Running the cell now. This output shows the distribution of the digit classes in the mfeat factors dataset, confirming that each digit, 1 through 10, where 10 represents the digit 9, is evenly represented with exactly 200 samples. This balanced class distribution is important for training fair and unbiased models, which is the key takeaway from this section where we explore our dataset's basic structure and target variable. Are there about the same number of samples for each digit? Let us confirm there are no missing values in the dataset. We ask if there are missing values. We sum up all missing, null, values in the data frame. Running the cell now. This output confirms there are no missing values in the entire mfeat factors dataset, which is important because it means we don't need to handle incomplete data before analysis. Notice how this aligns with our understanding of the dataset as fully numeric and clean, allowing us to proceed directly to modeling and exploration without pre-processing for missing data. Why is it good that there are no missing values for our classification task? Now let us separate features from the target column and convert class labels from 1 to 10 to 0 to 9. We remove the class column from our features. We convert the class labels to integers and adjust the range so the labels become 0 to 9. Running the cell now. Why might we want numeric labels from 0 to 9 instead of 1 to 10? Let us split our data into train and test sets using an 80/20th split. Stratify ensures each digit is equally represented in both sets. We split the features and target variables into training and testing datasets. We specify the test size as 20%, keep the class distribution balanced using stratify, and set a random seed for reproducibility. We close the train_test_split function call. We print the number of samples in the training set and the test set. Running the cell now. This output confirms that the dataset was split into 1,600 training samples and 400 test samples, maintaining the original class distribution due to stratification. Noticing the sizes aligns with our intent to reserve 20% of data for testing, ensuring enough examples in both sets to effectively train and evaluate our digit classification model. Why do you think we separate data into train and test sets? Next, let us scale our features so each has zero mean and unit variance. This improves model performance, especially with many numeric features. We create a standard scaler to scale our data. We fit the scaler on the training data and transform it. We apply the same transformation to the test data. Running the cell now. Scaling is often overlooked. Why might this matter for logistic regression? Let us train a basic logistic regression model on our scaled features. We create a logistic regression classifier and allow up to 200 iterations. We train the classifier using our training data. Running the cell now. This output confirms that the logistic regression model has been successfully created with a maximum of 200 iterations and a fixed random state for reproducibility. The model is now trained on the scaled features and target digit classes, preparing it to classify handwritten digits based on the numeric patterns in the dataset. This step is essential as it connects our numerical data to a predictive algorithm, moving from understanding the dataset to building a classifier. Try changing the max_iter value and check if anything changes. Now, let us make predictions on the test set and evaluate accuracy. We use the trained classifier to predict digit classes for the test set. We calculate the prediction accuracy. We print the accuracy of our simple model. Running the cell now. The output shows a high accuracy of 0.97, indicating that our simple logistic regression model is correctly predicting the handwritten digit classes most of the time. This accuracy confirms that the numeric features extracted from the images effectively capture key patterns for classification. It highlights the value of understanding our dataset structure before moving on to more complex models. Is this accuracy higher or lower than you expected? Let us print the full classification report to see precision, recall, and F1 score for each digit. We print out the classification report. The report shows precision, recall, F1 score, and support for each digit class. Running the cell now. This classification report summarizes the model's performance on the mfeat factors test set, showing precision, recall, and F1 score for each digit class from 0 to 9. Notice that scores are consistently high, around 0.95 to 1.00, indicating the model accurately recognizes most digit classes with balanced precision and recall. This reinforces the effectiveness of the numeric features in representing the digits for classification, an essential step in understanding and validating our dataset. Which digit is hardest for the model to classify? Why might that be? Visualizing the confusion matrix helps you see where the model is making mistakes. We calculate the confusion matrix using test labels and predictions. We create a new plot with a set figure size. We use Seaborn's heat map function to draw the confusion matrix. We label the x-axis as predicted. We label the y-axis as actual. We add a title to the plot. We improve layout with tight_layout. We save the plot as a conf_matrix.png. We close the plot to free up memory. Running the cell now. Let us open the confusion matrix plot to visually analyze the predictions. Are there more errors between some digits than others? What could be causing this? Let us visualize what the logistic regression model has learned about each digit. We extract the model coefficients. We start a new matplotlib subplot. We show the coefficients as an image, with colors reflecting strength and sign. We add a title to the plot. We label the x-axis as the feature index. We label the y-axis as the digit class. We use tight_layout for clean plots. We save the plot as a conf_matrix.png. We close the plot. Running the cell now. Let us visualize the learned feature weights for each digit class with this coefficient plot. Why do you think some features are more important for certain digits? Let us look at some sample predictions to see how specific test cases are classified. We choose 5 random samples from the test set. We select random indices without replacement. For each chosen sample, we collect the predicted digit class. We get the true digit class. We print the sample number and the corresponding predicted and actual values. Running the cell now. This output shows 5 random test samples where the predicted digit labels perfectly match the actual labels, confirming our model's accuracy on these cases. Notice the consistency between the predicted and actual classes, which are integers from 1 to 10 representing digits 0 to 9. This step helps us verify that our classifier correctly interprets the features from the mfeat factors dataset before moving on to broader evaluation. Try rerunning the cell and see if predictions change. If not, can you explain why? Here is a quick demonstration of what happens when the data contains missing values by mistake. We copy our scaled train data to create a new dataset with noise. We deliberately introduce nans in the first column to simulate corrupted data. We start a try block to handle any errors that arise during fitting. We instantiate a logistic regression model with specific parameters. We attempt to fit the model using the corrupted data. If an exception occurs during fitting, we catch it and print the error message. Running the cell now. This output highlights that the logistic regression model cannot handle missing values, nans, in our feature data, as shown by the introduced nan in the first feature column. The error reminds us that when working with datasets like mfeat factors, which have no missing values initially, it's crucial to either pre-process to impute or remove nans, or choose models that natively support them. This reinforces the lesson's emphasis on understanding data quality before model training. What kind of error did you see? How would you fix it if it happens in your own project? What if the feature data types are wrong? Let us force an error by setting them to string. We use a try block. We add a comment explaining that we use string instead of numeric data in features. We create an incorrect feature set by converting features to strings. We try to fit the model with string features. If an exception occurs, we catch it. We print the exception message. Running the cell now. Why is keeping numeric types in your feature set so important for models like logistic regression? Here is a simple check that your features have mean 0 and unit variance after scaling. We comment that scaling is best practice. We create a new standard scaler. We split the data again for demonstration. We fit the scaler on training data. We check the mean of the scaled training features. We check the standard deviation of the scaled features. We print the rounded mean. We print the rounded standard deviation. Running the cell now. This output confirms that the standard scaler has properly standardized the features, centering them around zero mean and scaling to unit variance. Notice how the mean is effectively 0 and the standard deviation is 1, which is crucial for improving logistic regression performance on high-dimensional numeric data like mfeat factors. This step ensures each feature contributes equally to the model, preventing bias from varying feature scales. Practice: always check your scalar output before modeling. The mean should be about 0. Wrapping data processing steps in functions makes your code reusable and reliable. We comment that wrapping is a common pattern. We create a function preprocess_data to handle feature and target extraction and scaling. We drop the class column to get the feature set. We convert the target classes to zero-based integers. We create a scaler for standardizing features. We scale all features using the scaler. We return the scaled features and target arrays. We run the function on our data frame to get processed data. We print the shape of the scaled features. We print the first 5 target labels to verify. Running the cell now. The output confirms that our scaled feature matrix has 2,000 samples and 216 numeric features, matching the dataset's original dimensions. The first 5 target labels, now 0 indexed from 0 to 9, correctly represent the digit classes after adjusting from the original 1 to 10 labels. This shows our preprocessing cleanly separates features and targets and standardizes inputs for modeling. What are the benefits of using functions for repeated steps? Advanced example: let us try a more powerful classifier with random forests. We comment that this is advanced. We import random forest classifier from scikit-learn. We create a forest with 100 trees and fix the random seed. We fit the model on the training set. We use the model to predict on the test set. We calculate the accuracy. We print the result. Running the cell now. This output shows the random forest classifier achieving about 95.75% accuracy on the mfeat factors test set, indicating strong performance in recognizing handwritten digit classes. Notice that this high accuracy validates the effectiveness of using ensemble methods with scaled numerical features for this multi-class classification task. It demonstrates how applying advanced classifiers can significantly improve predictive results beyond simpler models. Consider, why might random forest perform better or worse than logistic regression in this task? If you enjoyed this hands-on lesson, subscribe to our YouTube channel for more step-by-step guides. Let us visualize which features random forest thinks are most important for classification. We comment this is advanced. We extract feature importances from the trained forest. We create a horizontal bar plot. We select the indices of the 10 most important features. We plot the top 10 importances. We label the x-axis with feature indices. We add a title. We use tight layout. We save the plot as rf_importances.png. We close the plot. Running the cell now. Let us look at the plot of the 10 most important features in the random forest model. Can knowing which features matter most help you simplify your model? Here is a dimensionality reduction example. Let us use PCA to visualize our high-dimensional data in 2 dimensions. We import PCA from scikit-learn. We create a PCA object with 2 principal components. We fit and transform the scaled training data. We start a new figure with a defined size. We scatterplot the first 2 principal components, colored by the digit class. We add a title to the plot. We label the x-axis as PC1. We label the y-axis as PC2. We add a color bar to map colors to digit classes. We adjust the layout to avoid overlap. We save the plot as subcar_projection.png. We close the figure to free memory. Running the cell now. Let us open the PCA projection plot and see if digit classes are visually distinct in lower dimensions. How well are the digit classes separated in just 2 dimensions? Here is a tiny end-to-end pipeline, from raw data to trained model and test accuracy in one reusable function. We comment that this is end-to-end. We define a function for the full pipeline. We load the dataset from OpenML. We select features and targets. We split the data into train and test. We initialize the scaler to standardize features. We standardize the train features using the scaler. We standardize the test features using the same scaler. We build a logistic regression model. We fit the model to the training data. We calculate the accuracy of the model on the test data. We print the test accuracy. We return the test accuracy. We call the function. Running the cell now. This output shows a high test accuracy of 0.97, indicating our logistic regression model effectively distinguishes between the digits based on the 216 numeric features. Notice how the pipeline included key preprocessing, scaling the features, and stratified splitting to maintain class balance, which helped achieve this strong performance. This validates that with proper preparation, even a simple model can successfully classify handwritten digits in the mfeat factors dataset. If you can run this whole function in just one line, you are on your way to building solid reproducible workflows. Like this lesson? Like and share our YouTube channel to help more learners discover these practical Python guides. Recap what you learned. How to load, examine, and preprocess mfeat factors digit data. How to train and evaluate classifiers including logistic regression and random forest. How to visualize confusion matrices and feature importance. Troubleshooting common errors and best practices for reproducible pipelines. Next steps, try experimenting with different models or more advanced feature selection techniques. Running the cell now. Which topics in this lesson do you want to explore in more depth? Great work completing this hands-on digit classification walkthrough.